let's have a look at transactions, schedules, and serializability. Formally, a transaction is a list of actions, and these actions can be read or write actions, and they access a certain database object. So let's call this database object O. Then we will write a read action concerning the object O as R and then O in brackets, and a write action on the object O we will write as W and then O in brackets. A transaction ends with either commit or abort. And if commit or abort are not relevant, then we will omit them. So for instance, an example transaction could be reading the object V, reading the object Y, writing the object V, writing the object C, and then ending with commit. The scheduler is responsible for deciding the execution order of concurrent database access. So here we see that we have 3 clients, and each of these clients accesses the database in parallel. So each client sends the actions to the database management system. So client 1 sends actions 1, 2, 3, client 2 sends actions 1, 2, client 3 sends actions 1, 2, 3, and then the database management system. So the scheduler decides in what order these actions should be executed on the database. So here we see that first the action from client 1 is executed, then an action from client 3 is executed, then again an action from client 3, then an action from client 1, and so on. So the scheduler is responsible in deciding in what order these parallel actions will be executed on the database. The scheduler is responsible for making a schedule. A schedule is a list of actions from different transactions. So intuitively you can think of a schedule as a plan on how to execute the transactions. In such a schedule, the order in which 2 actions from the same transaction appear must be the same as the order in which they appear in the transaction. So this is easier to explain on an example. So let's have a look at an example. We have 2 transactions. Transaction 1 reads V and then writes V. Transaction 2 reads Y and then writes Y. Now, which of these 2 is a schedule of these 2 transactions? Let's have a look. In schedule 1, T1 reads V and then writes V, so the actions appear in the same order as in T1, that's okay. In the same schedule, T2 first reads Y and then writes Y, so it appears in the same order as in the transaction, so this is fine. This is a schedule of these transactions. Now let's look at schedule 2. Here T1 first writes V and then reads V, and this is different from the order in which the actions appear in the transactions. In transaction 1, we first read V and then write V, so the second schedule is not a schedule of these transactions. The order of the actions in transaction 1 is not the same as in transaction 1. A schedule is said to be serial if the actions of the different transactions are not interleaved. So if the transactions are executed one after another. This is an example of a serial schedule. First T2 is executed and then T1 is executed. The actions of the 2 transactions are not interleaved. Usually, we want schedules to be at least serializable. A schedule is said to be serializable if the effect on the database is the same as that of some serial schedule. So why do we usually want schedules to be serializable? The reason is that if a schedule is serial, then it really is as if we are executing transactions in isolation, as if one user operates after the next, but they are not interacting in parallel. The actions are not interleaved. If a schedule is serializable, then the actions may be in parallel, but the effects of these actions is the same as if the users would not work in parallel, as if they would work after one another. So if a schedule is serializable, then we do not have the concurrency anomalies, dirty read, inconsistent read, lost update, and so on. To understand when a schedule is serializable, we need to understand when two actions conflict with each other. Two actions are said to conflict if they are from different transactions, they involve the same data item, the same object, and one of the actions is a write. So let's have a look at this schedule. Here we have a read of the object y. Here we have a write of the object y. These two actions do not conflict because they are from the same transaction. Here we have a read of y, and here we have a read of y. These two actions do not conflict because both of them are read actions. Here we have a write of y and a read of y. These two conflict because they involve the same object y, and one of them is a write action. So here we have a conflict. There's different types of conflicts. We have write-read conflicts. This is a write-read conflict. We first have a write and then a read. We also have read-write conflicts, and we have write-write conflicts. The write-read conflicts we will short denote as WR, the read-write conflicts as RW, and the write-write conflicts as WW. So such type of conflicts can cause a schedule to be not serializable. We have a write-read conflict between transactions T1 and T2 if there is some object y such that T1 writes y and afterwards T2 reads y. So first we have the write and then we have the read of the same object. If the first transaction T1 has not yet committed, then this is a dirty read. Let's have a look at this schedule and let's try to find all the write-read conflicts. Here we have a read. That's a write-read conflict starts with a write, so we don't need to look at this. Here we have a write of database object v. Do we have a read of v afterwards by some other transaction? No. Okay, so this is not involved in a write-read conflict. Here we have a write of y, and we have afterwards a read of y by another transaction, so this is a write-read conflict. We have a read-write conflict between transactions T1 and T2 if there's some item y such that T1 reads y and afterwards T2 writes y. This is called an unrepeatable read, because if T1 would try to read y again, it would get a different value. So T1 is operating on stale data. Let's find all the read-write conflicts in the given schedule. Here we have a read of database object v, and afterwards we have a write of database object v by another transaction. So we already have one read-write conflict. Let's look whether there are more. For this read, there is no more write of another transaction, and these actions are not followed by any other actions from the other transactions. So there are no more read-write conflicts. we have a write-write conflict between transactions T1 and T2 if there's some object y such that T1 writes y and afterwards T2 writes y. The write of T1 is overwritten by T2. Let's have a look at this schedule and let's try to find all the write-write conflicts. Here we have a write of object y. So let's look whether we have another write of object y by some other transaction. And indeed, there's one write of the object y by another transaction. So this is our first write-write conflict. Here we have a write of v followed by another write of v by another transaction. So we again have a write-write conflict. And these are the only write-write conflicts in the schedule. If you have two adjacent actions that are non-conflicting and belong to two different transactions, then we can swap these actions without changing the outcome in the database. So without changing the effect that the schedule has on the database. So for instance, consider this schedule. Here we have a read of object y, and in the other transaction we have also a read of object y. These two actions are adjacent, they are non-conflicting, and they belong to two different transactions. So we can swap them. This gives rise to this schedule, and this schedule has the same effect on the database. Likewise, we have here a read of v and in the other transaction a read of y. These are also non-conflicting, they concern different objects and both of them are reads. We can also swap these two, giving rise to this schedule. So also this schedule has the same effect on the database. We say that two schedules are conflict equivalent if they can be transformed into each other by a sequence of swaps, and we are allowed to swap adjacent non-conflicting actions of different transactions. Let's have a look which of these schedules are conflict equivalent. In order to transform schedule 1 into schedule 2, we need to swap these two actions. They are both read actions, so they are non-conflicting, they are adjacent, and they belong to two different transactions. So we are allowed to swap them, and then we obtain schedule S2. So indeed, schedule S1 and schedule S2 can be transformed into each other by a sequence of swaps. In this case, a single swap suffices. So S1 and S2 are conflict equivalent. Can we also transform S1 into S3? In order to do so, we would need to change the write of v with the read of v. We would need to swap these two actions. However, they are conflicting, they concern the same object, one of them is a write, so we are not allowed to swap them. So there's no way to get this read of v in front of the write of v by a sequence of swaps of non-conflicting actions. So it's not possible to transform schedule S1 into schedule S3. These two schedules are not conflict equivalent. And since S2 is equivalent to S1, also S2 cannot be equivalent to S3. A schedule is said to be conflict serializable if it is conflict equivalent to some serial schedule. So if the schedule can be transformed via a sequence of non-conflicting swaps into a serial schedule. In particular, this means that the conflict serializable schedule has the same effect on the database as some serial schedule. And hence, every conflict serializable schedule is serializable. The other way around does not always hold. There are serializable schedules that are not conflict serializable. Let's have a look at some examples. Let's look at these schedules and determine which of these schedules is conflict serializable. So we want to transform the schedule into a serial schedule. Recall that serial means that the actions of different transactions are not interleaved. So the transactions are executed one after another. Here we have an interleaving of the actions of different transactions. So the question is, can we swap some actions to transform this into a non-interleaved schedule? Here we have a write of the object v, then we have a read of the object v, so we cannot swap these two. These are conflicting. We have a read of v and we have a write of v. These are also conflicting, so we can also not swap these two. We have a write-read conflict and we have a read-write conflict. So in this schedule we cannot swap anything. We cannot transform it into serial schedule, so it's not conflict serializable. Let's have a look here. We have a read of v, a read of v. These are both reads, so they are not conflicting, so we are allowed to swap these two. And if we swap these two, then we immediately obtain a schedule without interleaving. Then we first execute T2, so we first execute read of v of T2, then we execute the read of v of T1, and then the write of v of T1. So by swapping these two, we obtain a serial schedule, so this is conflict serializable. Now the third example is a bit more complicated. Let's have a look. We have here a read of v and followed by a write of v. So we cannot swap these two actions. This read we cannot get behind the write of v. So this means that T2 must be executed before T3. Moreover, we have here a write of y in T1 and then we have followed by a read of y in T2. So we cannot swap these two actions. This means T1 must be executed before T2. So let's summarize. We know that T2 must be before T3 and T1 must be before T2. So if there is a possibility to transform this into a serial schedule, then we have to bring T1 in front, followed by T2, followed by T3. Let's see whether we can do this by some swaps. So can we bring T1 in front? We have a write of y and here we have a write of v. These are not conflicting because they concern different objects, so we can swap these two. Okay, now the write of y is one step further in front. The write of y does also not conflict with the read of v. Again, they concern different objects. So indeed we can swap T1 fully in front. So T1 is fine. Now we just have to consider T2 and T3. And as we said, T2 must be before T3. So the question is, can we swap this write of v all to the end? So this write of v, and here we have a read of y. So these two are not conflicting, so we can swap these two. And then we have a write of v and a write of z. These are also not conflicting, also concern different objects, so we can also swap these two. So indeed, we can swap T3 all to the end. So then we have a serial schedule where first we execute T1, then T2, and then T3. And indeed, we can reach this by a sequence of non-conflicting swaps. So this schedule is also conflict serializable. On the last slide, we've used a reasoning of the form because we have conflicting actions between T1 and T2, and the conflicting action of T1 appears first. If there is a serial schedule that is conflict equivalent to the given schedule, then in the serial schedule, T1 must appear first. And this kind of reasoning is made precise by what is called a precedence graph. A precedence graph is a graph whose nodes are the transactions, so the nodes are T1, T2, T3 and so on. And in this graph we have an edge from T1 to T2. If there's a conflicting action between T1 and T2, in which the action of T1 appears first. And it's very important to understand that we are now not only looking at adjacent actions, the actions can be arbitrarily far apart. The only condition is that they are conflicting and from different transactions. So let's have a look. Here we have a schedule with two transactions, T1 and T2. So we have a precedence graph with two nodes. So what are our edges in this graph? We have a conflict, a write-read conflict between T1 and T2, where the action of T1 appears first. So we have an edge from T1 to T2 in the graph. Also we have a read-write conflict, where the action of T2 appears first. So we have also an edge from T2 to T1 in this graph. So this is our precedence graph that belongs to this schedule. In the second schedule, we have only one conflict. We have a read-write conflict. And in this conflict, the action of T2 appears first. So we have again two nodes, T1 and T2. And we have one edge from T2 to T1. Now in our last example, we have two conflicts. We have a read-write conflict. So we have three nodes, T1, T2, T3, and we have an edge from T2 to T3. We also have another write-read conflict between T1 and T2, and the action of T1 appears first, so we also have an edge from T1 to T2. And this last example illustrates that we are considering all conflicting actions, no matter whether they are adjacent or not. They can be arbitrarily far apart. This and this action, they are conflicting, but they are not adjacent. Likewise, this and this action are also not adjacent. Nevertheless, they give rise to an edge in our precedence graph. We can use the precedence graph to decide whether a schedule is conflict serializable. So we have the following nice theorem, which states that a schedule is conflict serializable if and only if there is no cycle in the precedence graph. Here cycle really takes the directions of the arrows into account. We will later see an example of that, but first let's look at the three examples from the last slide. In the first schedule, the precedence graph contains a cycle. We can go from T1 to T2 and back to T1. So this schedule is not conflict serializable. Our second schedule does not contain a cycle in the precedence graph. So this schedule is conflict serializable, and we can serialize it in the following way. We can read this precedence graph as T2 needs to be before T1. So we first execute T2 and then T1, and this is our serial schedule. Likewise, in the precedence graph corresponding to the third schedule, we also don't have a cycle. We can read off the order of the transactions in the serial schedule. T1 needs to be before T2, and T2 needs to be before T3. So for the second and the third schedule, there are no cycles. So these schedules are conflict serializable. If there are no cycles in the precedence graph, then we can obtain an equivalent serial schedule by a topological sort of the precedence graph. So as already said on the last slide, the precedence graph gives us the order of the transactions in the serial schedule. So we can interpret this as follows, namely that we have an edge from T1 to T2, therefore T1 must be before T2. We have an edge from T2 to T3, therefore T2 must be before T3. And then applying a topological sort gives us the order T1, T2, T3, and we thus obtain a serial schedule by first executing T1, then T2, and then T3. Let's have a look at this example and let's try to decide whether the schedule is conflict serializable. So we're taking the schedule and we're constructing the precedence graph. We have 3 transactions, so the precedence graph has 3 nodes. Now let's see what edges we have in this graph. We have a conflict between the read of V and the write of V. So we have a conflict between T1 and T2, where T1 appears first, so there's an edge in the graph from T1 to T2. Likewise, we have a conflict between T2 and T1, where T2 appears first, so there also is an edge from T2 to T1. Moreover, this read conflicts with this write, so we have an edge from T1 to T2, and this write conflicts with this write, so we have an edge from T2 to T3. And also this write conflicts with this write, but we already have an edge from T1 to T3. So this is our completed precedence graph, and obviously there is a cycle. We can go from T1 to T2 and back to T1. So this precedence graph contains a cycle. This schedule is not conflict serializable. However, the schedule is serializable because we can execute T1 before T2 before T3, so in the order T1, T2, T3. The reason that the schedule is serializable is that these writes of T1 and T2 are overwritten by T3. So no matter that there is some interleaving, no matter what they are doing, we can simply execute this write after this, because anyway, no matter what this write and this write are, the result will be overwritten by T3. So the schedule is not conflict serializable, but it is serializable. It has the same effect on the database as some serial schedule. Let's have a look at another example. Let's determine whether this schedule is conflict serializable. We have 3 transactions, T1, T2, T3, so we get a precedence graph with 3 nodes, T1, T2, and T3. Let's have a look for conflicts. Here we have a read of V, does not conflict with the read of Y, but it does conflict with this write of V. So read of V and write of V conflict, so we get an edge from T1 to T2 in the precedence graph. Likewise, this read of V conflicts with this write of V in the second transaction, so we also get an edge from T1 to T2 in the precedence graph. And these 2 write actions conflict on themselves, so we get an edge from T3 to T2 in the precedence graph. There's one more conflict in this schedule, namely this read of Z and the write of Z. These 2 actions conflict, but we already have an edge from T1 to T3. So we don't need to add this edge again. So now let's look at our precedence graph. There is no cycle in this graph, although the undirected graph, so ignoring the direction, we have a cycle. But if you're looking for the cycle in the precedence graph, we mean taking the direction of the arrows into account. There is no directed cycle in this graph. So since there is no cycle in the graph, we can use the topological sort with respect to the precedence graph. What do we get? We see that T1 needs to be before T3 and before T2. So T1 needs to be in front. Moreover, T3 needs to be before T2. So we obtain a serial schedule that is conflict equivalent to the original schedule by executing first T1, then T3, and then T2. And the result is shown on the bottom. So the schedule on the bottom is conflict equivalent to the schedule on top. We can transform these schedules into each other by a sequence of swaps of adjacent non-conflicting actions. So let's practice a bit in the online system with serializability and precedence graphs. Here's our first task. We are asked to compute the precedence graph for this given schedule. So I will start by writing all the possible combinations of edges in this graph that we may have. We might have an edge from T1 to T2. I will put a question mark because we're not yet sure. We may have an edge from T1 to T3, from T2 to T1, from T2 to T3, and from T3 to T1 and T2. Okay, that's the possible edges that we might have. Now let's step by step check whether the edge should be there or not. We start with the edge from T1 to T2. Okay, we look through the actions of T1. Let's start with the right of B. Is the right of B followed by an action in T2 that conflicts with this? A right of B or a read of B? No, it's not followed by a right of B or a read of B. Here we have a read of D in T1. Is this followed by an action in T2 that conflicts? No, also not. So there's no edge from T1 to T2. So we can erase this part. Now let's check whether we have an edge from T1 to T3. We have a right of B, and this immediately conflicts with this right of B in T3. So indeed we will have an edge from T1 to T3, because there's an action in T1 and T3 that conflict with each other, and the action of T1 comes first. Okay. Next we check whether we have an edge from T2 to T1. Here we have a read of B, and this read of B in T2 is followed by a write of B in T1. So we indeed have a conflict where the action of T2 comes first. So we will have an edge from T2 to T1. Next we check whether we have an edge from T2 to T3. We have here a read of B, and there is a write of B. So we will have an edge from T2 to T3. There's multiple reasons for that. We have also this write of C followed by a read of C and by a write of C. So also this would give rise to an edge from T2 to T3. Okay. Next, let's check whether we have an edge from T3 to T1. We have a write of B, and this is not followed by a write or read of B in T1, and these two actions are not followed by anything in T1, so we don't have an edge from T3 to T1. Finally, we check whether there's an edge from T3 to T2. We have a write of B, not followed by a read or write of B in T2, write of C, not followed by an access of C, and this is not followed by anything, so we don't have an edge from T3 to T2. Okay, so this is our precedence graph. We have an edge from T1 to T3, and from T2 to T1 and T3. Let's check. Yeah, our solution is indeed correct. And remember that you can always continue practicing, so you can simply say that I would like to continue practicing on another example, and you will get another schedule to practice on.